lead wave interactions?
Yeah, so we're I'm going to give you a little bit of very qualitative overview of some experiments that we've been running with the configuration in the lab that's up the hill in the geophysical fluid dynamics lab. And what we're aiming to do is understand the interactions between sort of the eddies and sort of background rotation and lee waves in what we've got, what we call this large rotating annulus, which is figured here, and I'll talk about it in just a sec. So lee waves in climate. So we haven't really heard a lot about them in the last couple of days. So I'll just give you a quick intro, just in case anyone isn't totally across the board with them. So lee waves occur when you've got stratified flow going over topography. And what we've got pictured here is, I guess it's from a satellite, and I guess this is some sort of flow that's coming up from the bottom left corner of this page, so some sort of airflow, and it's interacting with the coastline, and the coastline's got some sort of topography. And what you're visualizing here are in these cloud bands are lee waves that are sort of being generated by this stratified flow interacting with the topography. I wanted to find a photo of lee waves in the ocean, but it's kind of difficult to find those photos. And lee waves, the propagation of lee waves is real sort of Goldilocks situation where the flow needs to be not too fast or not too slow. If it's too fast, it just leads to localized mixing. If it's too slow, then nothing happens. The stratification needs to be not too stratified, but also not too weak, not too mixed. And then the topography itself needs to be of the right scale as well. And if you meet all these conditions, then you're actually able to generate propagating lee waves. And when they do propagate, they're able to transfer momentum through the water column or through the air column vertically and laterally, as well as momentum as well as energy. And ultimately they can lead to turbulence and mixing when these lee waves break. So how the lee waves have been studied in the ocean before, usually you end up, you set up a very long linear tank. So one of the tanks that we've got up the hill is probably the size of this screen, like in length, and probably this sort of high. And it's a long linear tank. It's not rotating. You fill it up with a salt stratification. Filling that takes 6 hours. You kind of have to babysit it while it fills because it's always a fiddly process. And then once you've got that stratification, you drop in a piece of topography like this. This is something that Van Dossman did while he was a postdoc and a visitor here. He'd drop in this piece of topography that would sit at the surface. So this image is upside down. He'd put it in at the surface and then drag it across the stratification. And you'd end up, if you meet the right conditions for propagating lee waves, you end up with these lee waves in the lee of the hill. And as you can see, there's a lot of mixing and turbulence that's associated with it. So your stratification that you've built over many hours is very quickly destroyed, and you empty the tank. You take a lot of measurements over about 20 minutes and then empty the tank and go home and come back in the next day and do it all again. And you get one data point out of your day's worth of work. And these experiments are incredible. They allow us to identify the conditions under which your lee waves are propagating and mixing is occurring, and then also quantifying how much mixing is actually occurring. Obviously in this situation, if you've got the lee wave, if you've got the topography that's being dragged across the tank, it doesn't make a difference whether you drag it that way or drag it this way. Okay, so that's the nice linear lee wave case where most of our understanding of lee waves and lee wave mixing is sort of come from. What we're hoping to do is include the effects of rotation into that system. And we do so with what we've been calling this large rotating annulus, which is essentially, Ivan's tank, but we've wrapped it around on itself, and that's what we've got. That's what I've got just here. So I'm going to point out some features of this tank. The first is we've got the ability to control the temperature of the sidewalls. So this outer jacket, which is kind of this sort of thickness, it's probably this thick. I should say this tank is 1.6 meters in diameter, inside diameter. This outer jacket is it's filled with water for a number of reasons, but we can use that water we can control the temperature of that water, and we use that to impose a sidewall boundary condition that can be hot or it can be cold. And we've got a similar system in the center of the tank where we're constantly flushing water of a constant density through this isolated region in the center of the tank. And again, we control that temperature to be hot or cold, depending on what we want. And the idea is that we're able to get a temperature difference across the radius of this annulus. And having a temperature difference or a thermal gradient across there allows us to get, hot water and cold water that's sort of coming into the tank, and depending on which configuration you go with, the hot water will go to the surface, the cold water will go to the bottom, and we'll maintain a stratification through this through the water body. In addition to the stratification, we also need a bit of topography. So what we've got here, I'm just trying to highlight here with the parallax issue, is this topographic ridge. So in this configuration, it extends the full width of the annulus, and it sits at the bottom of the tank. What we've got, what we're able to do is we've got a motor that drives a ring that is fixed to this topography. So this motor actually rotates the topography around the annulus while the annulus is spinning. I'll show you a video of that in just a second if that's not totally clear. And in addition to, so how we actually quantify, our diagnostics package, if you like, is a thermistor array, which we're able to profile. So it's on this big swing arm that we're able to profile across the tank, and then also sort of make some measurements like profile vertically in order to build an idea of the thermal structure throughout the fluid. And then we've got a thermal camera, which is sitting above the table, probably 3 meters above the table, and looking down onto it. And we're able to see the sea surface temperature of our system. So the control variables that we've got in this configuration is the rotation rate of the table, the temperature difference across the tank, the ridge velocity, so able to rotate this ridge around in either direction, and then we've also got the ridge geometry. So we've got standard size ridges or tall ridges or whatnot. And I will try to show you what it looks like in real time. So this is the table right now. So what's being logged here are the temperatures. This is not the ridge configuration. This is a slightly different configuration where we're moved on from the ridge and we've actually just got a seam out. So instead of having a two-dimensional ridge that extends across the tank, we've just got a single seam out that sits in the middle of the tank, and that seam out is being rotated around the tank. So you can see here, this is off the color scale. This is cold in the center, and it's hot at the outer edge. And this is rotating at the moment. This is the swing arm array that's got the thermistors sort of attached to it. And this ring that has some of these little rollers, if you like, that the ridge is actually rolling on. The ridge is rolling around, and right here is what we use to connect the seam out to the ridge. So if you just go radially inwards from that, you'll see the seam out, and it's probably about here in this point. But what's clear in this case is that there's a lot of turbulence that's already in the system, a lot of eddies and variability, and then what we're doing is sort of adding to that with the differential rotation or the differential velocity that's associated with the seam out. So, any questions so far? Yeah.
Can you oscillate the seam out?
Yes, we can. We started doing that, and then we need to understand the steady case first. Yeah, but
Why is the water green?
this is a thermal image. So,
No, the real water. In the picture of the tank.
oh, so you can see it. Yeah. Yeah, if it's clear, then it's hard to convince people that it's actually water there. Okay, you've all got phones. So if you want to take a look at what the thermal image looks like, I'll show you a video of this. So it's not green. Okay. So what we've got here is a case where I've sped it up a little bit. This is the ridge case. You can obviously see that the ridge is rotating around the tank here, and there's quite a bit of variability in there. This wake that's coming off the ridge is what we're looking for. These are the lee waves in the rotating frame of reference, and surprisingly, they're not two-dimensional. There's a lot of three-dimensional structure in there. What we do want to do with this, though, is we want to fix the ridge. Like, we want to get into a frame of reference where the ridge is stationary, because that's like easier to understand, I guess. So what I've done there is I've actually just fixed the ridge. So the ridge is here, and what I'm doing is rotating the image around this fixed ridge. So this gives you maybe give you a better idea of what these lee waves look like in this sort of, well, it's the surface expression of the lee waves in this particular case, which is one of the things we do with this thermal data is we're able to look at the magnitude of the sea surface temperature gradient, which gives us a proxy for how much mixing is taking place at the surface in this instance. And you can kind of see that, most of the mixing is occurring in the lee here, and then there's a lot of sort of this residual high gradient sort of structure that continues throughout and might dissipate a little bit, but most of the action is taking place where the ridge is. And then another diagnostic that we do is looking at the Laplacian of the sea surface temperature, which gives us a proxy for the vorticity. And that's also something that we're going to try to understand. And you can see, there's sort of this banded structure that's coming off the ridge in these instances. Okay, so go back to what we've got here. Okay, so just to reiterate the parameter space that we've got, the main parameters that we're changing are the temperature difference across the tank. So whether this is hot in the center or cold in the center, so the direction of this thermal gradient. The reason why we change the direction of this thermal gradient is, you've got this thermal gradient that establishes through the thermal wind balance a geostrophic flow, and the geostrophic flow can be cyclonic or it can be anticyclonic, and it turns out that actually makes a difference. And then another parameter that we're changing is the ridge velocity, and we're also changing the direction of this ridge velocity. So it can also go cyclonic or it can go anticyclonic. The thermistor array, we tend to have it located at some point where we just park it, and the 4 thermistors are at different depths throughout the tank. And then we've got the ridge that comes and moves underneath the tank. So while the thermistors are stationary in the frame of reference of the tank, because the ridge is moving, they're actually everywhere in the tank. And then, we've got control over the rotation rate and geometry of the ridge as well. So we've got quite a large parameter space that we're trying to explore and trying to make sense of. So now this is a point that I wanted to sort of make a little bit clearer. So if you have cold in the center and hot at the outer edge, the geostrophic current that establishes from that thermal configuration is cyclonic. If you have hot in the center and cold at the outer edge, it is anticyclonic, okay? And then we've also got, so in this sort of, quadrants, we've got the direction of the geostrophic current, and then we've got the direction of the ridge. So this gives us 4 different regimes.
Does that mean your tanks are in the northern hemisphere?
No, I'm always spinning it in the southern hemisphere. But because we're changing the direction of the cyclonic and anticyclonic, But what I would like to know, and this is a question for anyone here, where is the Southern Ocean in this quadrant space? That's a real question. I'd like to know. So we can rotate the ridge cyclonically or anticyclonically, and we can have the thermal forcing. So that's cyclonic as the top and anticyclonic as the bottom. So that's the direction of we're rotating the ridge. And then the direction of the geostrophic current depends on the direction of the thermal gradient across the tank. And so that can be cyclonic or anticyclonic. And so that's whether it's right or left here. So these give us 4 regimes. Yeah. Yeah.
How large is the tank?
We can get it to maybe 20 degrees before we lose too much heat to the lab. Yeah, but we generally tend to run it maybe 10 or 15 degrees temperature difference. So it's a pretty weak temperature difference, but it's enough to give us a stratification and it's constantly maintaining the stratification while we're destroying the stratification with the ridge and the turbulence that's in there. It reaches a steady state, a statistically steady state, where the stratification is maintained indefinitely. Okay, these 4 different regimes can have the same absolute bottom velocity, the same stratification, and the same ridge geometry, which are the 3 terms that go into parameterizing Lee wave mixing in ocean models when they do parameterize Lee wave mixing. Okay. So we're gonna, this is 2 hours of logging of the temperature of that thermistor array, with the red one being closer to the surface and the blue one being closer to the bottom. All of these wiggles that you can see in there are obviously variability in the temperature, and the fact that most of them, occur at all depths kind of gives you the sense that this is a lot of what we're seeing is in here are barotropic features. There's a little bit of baroclinic features. This is just 2 hours of logging, but what I can do is like each like big blip that's in here is the ridge passing underneath the thermistor rack, the thermistor array. So what I'm going to do is I'm going to take this time series and break it up into ridge oriented space. So where the ridge is, and that's what I've got here. So I'll bind these temperatures by the location of the ridge. So each of these bins in, like as you go around the tank, is around the annulus. Each of these bins probably has, I don't know, maybe 30 data points in it. So it's quite a long time series in terms of what it is that we're looking at. Where it's flat, where this average is flat, that's kind of saying that all the variability that's going on in there is just random eddies, turbulence. Where you've got a coherent feature, that's saying that every single time the ridge comes past, this is the signal that this is the temperature signal that's taking the thermistors are saying. Yeah.
So it's like a snapshot of what the ridge is doing.
At any given time in here is a snapshot. This is sorry, the term escapes me. It's like an ensemble of like I've taken like so the ridge takes maybe 2 minutes to do a lap around the tank, and I've taken it's actually maybe close to 5 minutes. I've taken every 5-minute section and binned it by where the ridge is relative to where the thermistors are. So in this instance, we don't actually know where the ridge is, but here obviously the ridge is going to be about here, and it's moving this direction. So it's going to be here and it's moving this direction. And these are the lee waves that the ridge is kicking off in the lee of the ridge as it's moving this way. And to give you a visual of what that actually looks like, I'm just going to go back to Ivan's nice picture here and just sort of show that I think this is what we're looking at. Okay. So hopefully I'm convincing you that we've got lee waves in this particular case. And in this particular case, we're meeting all those Goldilocks criteria for where we've got propagation of lee waves. So I'm not really going into the details of what that particular case is, but anyway. Now, if we do the same conditions, but put those into those 4 different quadrants of where the ridge velocity, the direction of the ridge velocity and the direction of the thermal gradient, we end up with these 4 sort of figures. So this was the one that you were looking at just before, where the ridge is here and these are lee waves. When we go to, basically what this figure is showing is that the direction of the ridge and the direction of the geostrophic velocity is making a difference to how we actually, or the characteristic structure of these lee waves. I'm running short on time, so I'll just, these should be the same. Yes.
Just a very question, investment grade, and you've got wall center and all that, so is that 2 and 4?
2 and 4, yes. Yeah. Yes. Okay. So what does the surface temperature in these different cases look like? Well, they're also wildly different. Let's go. So they're also wildly different here in these 4 cases. Come back. So yeah, these are cases where they've got identical bottom velocity, identical stratification, and identical ridge geometry, but well, here the surface expressions of these the temperature field is obviously incredibly different between these 4 different cases, but these would be parameterized by ocean models in as you know as being the same. So there's some dynamics here that we're missing, and we would like to understand what they are. The difference is the ridge is rotating cyclonically or anticyclonically, and the thermal gradient is either going into the tank or it's coming out of the tank. And these are properties or parameters that are just, you know, that shouldn't make any difference by the 2-dimensional non-rotating theory that we've developed, or that we're aware of. So anyway, very different circulations, and would like to understand what's going on. And I think that's probably, yeah, that's it. So yeah, rotation is obviously very important for these Lee wave dynamics. They're not 2-dimensional structures, obviously, and yeah, characteristically different structures to the flow that depend on parameters that haven't been incorporated, haven't been even thought about to include into our understanding of Lee waves. So, thank you.